Hello everyone. In today's lesson, we're going to continue connecting word problems and exponential functions. Our goal for today is to think about how can we connect the knowledge and ideas we've mastered regarding growth and decay functions so far to these more real-life scenarios, which actually are related a lot to growth or decay equations, and we'll be looking at the base a lot and seeing if this matches growth and decay and hopefully making a lot of those connections. So to do this, we didn't finish yesterday's notes. You're going to have to reopen yesterday's notes or download it if you didn't have your device yesterday. It's going to be posted under 21826 yesterday. You're looking to find this on Canvas or reopen it or open up your Notability app. And yesterday we did several things. We started out with a brain dump, then we went to the whiteboards for a couple things. Then we talked about percentages and writing them as a ratio of the part divided by the whole and how we could come up with the decimal equivalent. And the whole purpose of that was because when we're trying to find a percentage of something, we're multiplying by that decimal equivalent. So if we're multiplying by the wrong decimal equivalent, then that's not going to help us in achieving what we want to achieve, such as like finding the price of a TV when it's on discount at Target, right? So here's two more problems where we're going to find a percentage of something and multiply by its decimal equivalent. Something else I'd like you to keep in mind is this problem going to be a growth problem or is this problem going to be a decay problem? And what do I do with that amount that I find after I multiplied by its decimal based on what the problem is doing? So let's look at our first problem over here. A pair of slippers typically costs $18. They're on sale for 20% off. How much can I expect to pay? Let's not include tax for this problem. So we've got a couple pieces of information that we need to decipher. Information number one is like we have the price, right? So we know that the price of the slippers right now is $18. We also know that they're on sale for 20% off, right? And so I'm going to need, here's my percentage. I'm going to need my decimal equivalent for 20%. So we know it's the part divided by the whole, and that's going to give me 0.20 in my calculator. Okay, so that's the decimal. And again, if we're following these directions, when finding a percentage of something, we're going to multiply its decimal equivalent. So obviously I'm talking about the price of the slippers. So I'm going to take 18 and multiply it by the decimal, 0.20. Now, if I run this into my calculator, 18 times 0.20, I get 3.6. Or we're talking about money, so I'm going to put $3.60. Okay. Does this mean that the cost of my slippers is $3.60? No, that means how much they're on sale. So I'm going to take off $3.60, right? So since it tells me that they're on sale for 20% off, specifically like this word off, I know that I'm going to take my original price of $18. And since they're on sale, I'm going to take away $3.60. And when I do that, that leaves me with the actual price of 14.4 is what my decimal says. But remember, this is money, so I'm going to add a zero. $14.40. Whenever we're dealing with money, we're going to want two decimal places, all right? Two decimal places. The next problem is slightly different. It's not necessarily going to be about the price of something or if something's on sale, but rather a sports team. So last year, the Miami Dolphins won 10 games. Next year, they're hoping to win 30% more of those games. How many games are they hoping to win in total, right? So these two questions are similar but different. Notice that for the first problem, it was like, how much can I expect to pay for the slippers? And we got $14.40. And this question says, how many games are they hoping to win in total, right? So let's start off with what we know right now. We know that they won, 10 games last year, right? And our goal for this problem is they want to win 30% more games. So they want to win 30% more, right? There is our percentage. We're going to need to turn it into a decimal equivalent. So we're do the part divided by the whole, which is going to give us 0.30, okay? And I know when I find a percentage of something, I want to multiply the equivalent. So I'm going to do 10. That's how many games that we have, times 30% that we want to win more. And when we do that calculation, we end up getting 3. So again, that doesn't mean that they're going to win 3 games next year. That's not more games. If I'm comparing how many they've already won, that's 10, the number I got is smaller than that, so that doesn't make sense. So since we want to win more games in the future, I'm going to take my initial amount of games that I have, 10, and since I want to win more of them, I'm winning 3 more games as my goal, so they're hoping to win 13 games total in the future. Answering that question. So something you'll notice that kind of pops up and seems very subtle, but it's actually a pretty big deal, is if something's on sale for 20% off, right? When something was on sale, we had to minus that amount. But if we were looking to find something more, 30% more, I took this amount and I needed to add it to my initial amount. So hopefully you're starting to pick up on that. Here's 2 more scenarios where they're going to behave similarly, but I'm going to ask us first to decipher if the problem is going to give us things that are increasing or the problem is going to give us things that are decreasing. So the first problem says the population grew by 7%. Last year it was 120,000. What is it now? So the first question I want you to pause and think about is this increasing or is this decreasing, and how do we know? Okay, it says the population grew, which we know, growth and decay, that's things that are increasing, right? So it's growing by 7%. Perfect. First, we have to start out with how much does it have initially, right? Or to start. The population says that it was at 120,000, right? And we also know that it's growing by 7%. So that's kind of like this cool rate that we have. So we're going to grow 7% out of the whole 100, and that's going to give me 0.07 as the decimal, okay? And if the population, the initial amount, is growing by 7%, is that addition or is that subtraction? Right, it's going to be growing, so it's going to be addition. I'm going to start off with how much I had originally, 120,000, and I'm going to need to add that 7%. But oops, I forgot to find the 7%. Hold up, wait a minute. Let me just move this down here for a second. I need to find that amount. So let me do that first. If I know I have 120,000 and it's growing by 7%, I need to multiply by 0.07. Remember that when you're finding a percent of something, you're multiplying, and 7% of 120,000 is a lot. Punching that into my calculator, that's 8,400. So that is exactly how much I'm going to add to my starting amount of population. And when I do 120,000 plus 8,400, that gives me 128,400 in the population. Okay, so you might start to notice something between these problems. We start off with what information do we know, such as the price, the sale percentage, the games, the win percentage, the population, the growth percentage. And then for all of these problems, you'll notice that we did this. The initial times the value, the initial times the percent value, the initial times the percent value. And once we get that number, that's what we're adding or subtracting to the initial amount. All right, let's talk about Grandma Cindy. Okay, so Grandma Cindy shrunk by 5%. She used to be 65 inches tall. I want to know, how tall is she right now? So first and foremost, is this growth or is this decay, and how do we know? This is decreasing or decay because she's shrinking by a certain percentage. So let's start off with what we know. How tall was Grandma initially? Well, it says she was 65 inches tall. So 65 inches. All right. Then I know that she had a rate of shrinking, right? So I know that she shrunk by 5%. And I need to get that as a decimal equivalent. So I do the part divided by the whole. The whole is 100. And that gives me 0.05 as my decimal, which is what I'm going to use. Then I'm going to take my initial amount, which is 65 inches. I'm going to multiply by my decimal equivalent, 0.05. And when I do that, I end up finding the number 3.25. Now, obviously, if Grandma shrunk by 5%, she didn't go from 65 inches down to 3.25 inches. No, because she's shrinking, right, that's going to be a loss in inches. And since that's a loss, from my starting initial height, I'm going to take 65. And since she's shrinking, she's getting smaller. So I'm going to subtract those 3.25 inches. And when I do that, I get my final height of Grandma after 1 year, which happens to be 61 inches, 0.75. Something that I want to encourage you to do with this lesson is to write out what your answer means in words. So like, for example, the last one I wrote 128,400 in population, like that's what my population is now. The answer we just got for Grandma is 61.75. That is her height right now. So I'm reminding myself of the context. In the problems previous, I wrote 13 games total. That's how many games we're hoping to win, right? And then for the first one, 1440, that's the cost of the slippers on sale, right? And again, depending on the context of the problem, right, if something is growing, we ended up adding that amount. Something is decreasing, we ended up subtracting that amount. So essentially, how does this relate to growth or decay, right? When something is changing exponentially, it's being multiplied by that same factor over and over and over again, repeatedly, right? And in comparison to something not growing at all, that is just like multiplying by a baseline of 1. So we're going to see what I mean by this like baseline of 1 and how that comes into play to our exponential growth and decay problems. Okay, so I have a growth problem in the middle column and a decay problem in the right-hand column, and hopefully we'll start to see what's going on here, right? So Mateo, he invested $500 and it's growing at a rate of 4% each year. We know that this is growth because it says that it's growing. Typically, when you invest money, it grows, okay? It can lose money, but typically the purpose of why people invest money is so that it gets larger. So it grows at a rate of 4% each year. So how much is it worth after a single year? So we've got some information here, right? We know for starters that the initial amount of money that Mateo has is $500, right? And we also know that his rate is 4%. Got to get our decimal equivalent, so the part divided by the whole gives me 0.04. And I know if I want to find out how much money I'm going to have after a year, I'll do the usual. I'll take my $500, I'll figure out what 4% of that is. 500 times 0.04, as it turns out, is 20. So again, since this is growing, my money is growing, I'm going to actually end up taking my $500 and adding the 20, and that gives me my final amount of $520 after 1 year. Right, so writing the words, giving context to the problem. Now, where this starts to get more and more interesting is how much would it be worth in 15 years? So it's still that $500 that we're starting out with. After 1 year, Mateo has $520, right? Then I'm going to take $520, and that's going to grow at 4% that year. I'll figure out what that is. I'll add that to my 520 and keep going and going and going. And it's kind of like this endless loop of calculations, right? So let me show you what I mean. So if that's at the after year 1, if I'm moving into year 2, now for year 2, I have $520. I still have my rate of 4%, so that's going to be 0.04. So I would perform the same calculation. I'm going to take 500, nope, not 500. I'm going to take 520, sorry. I'm going to multiply it by 0.04, right? And that will give me how much my money grows at year 2, right? So when I do that, I get 20.8. It's a little bit bigger, right? So now I'm going to have to take my $520 and I have to add my $20.80 and get my final amount of $540.80 after year 2. And then I would repeat the process again. So where this would go over here, that's my new amount going in to year 3, right? I have $540.80. I'm going to multiply that by my rate of 4%. When I do $540.80 times 4%, I get 21.632. And then I'm going to have to add it to $540.80, so 21.632, and that's going to be my amount, right? Over and over and over again, all the way for 15 years worth. This is just like that problem that we started off the unit with, that we found the shortcut for yesterday, right? If we think about it, my initial amount is kind of changing, but we're doing the same process. We're always multiplying by our same rate. We're always multiplying by that 0.04. And because we're taking those values, right, this 520, this guy kind of popped over here. Then I did my calculation, got that number, popping it back in. The shortcut way of doing this, instead of going through all of this work, which is great and fine and dandy, but what I could do instead is if I wanted to find out what I'm doing in 15 years, I can think about this exponentially because it's growing a little bit more and a little bit more and a little bit more, right? If I'm thinking of it in context of A times B to the X, we know that this is growth, right? So my base right here, my base is going to be a number bigger than 1, and it's growing by that 4% rate, right? So coming back to my baseline of 1, right, and I'm multiplying by the same factor repeatedly, right? I'm going to start with my initial amount, my $500. But if I was to say my base is 0.04, you guys would tell me, hey, that is not a growth base. That is not a base larger than 1. So to get our growth base, we're going to do something kind of tricky. We're going to start with 1, and we're going to add, because it's growth, 0.04. Just like we were adding things earlier when they were growing, right? When we were increasing the number of games. And then we have the exponent, right? So we have to the x, right? But if I want to find out how much I'm spending after 15 years, then I can replace my x with the number 15. Now, to do this and actually figure out how much money I do have, we're going to have to use PEMDAS, the order of operations, right? PEMDAS. That says we have to do our parentheses first, which let's simplify this. This gives me 1.04 raised to the 15th power, and the 500 was in front. And now we're ready to do the exponent, right? 1.04 raised to the 15th power. In your calculator, if you're going to do 1.04 raised to the 15th power, that is going to be a crazy decimal. It's like 1.80094350551, right? 1.04 to the 15th. If I was going to do that here, 1.04 raised to the 15th power, right? It's a really big decimal. I don't want to write all of that stuff out, but I've done the exponent. Then the next part of PEMDAS is to multiply. So I'm going to multiply 500 times that amount that I just had, right? So now I'm going to multiply by 500, and I get this amount, 900.47175727, like all of these things, 900.47. So ultimately, let me give myself a little bit more space here. This ends up giving me 400 point, what was my decimal again? Nope, that's 900.47175. 47175. Now, if I'm investing money, we also got to talk about rounding. So to round, we have 2 decimal places. I like to put a box around it. You look to the third to figure out if I'm going to keep it at 47 cents or if I'm going to increase it to 48 cents. If the numbers are 5 or below, we keep it. So my final answer here is I'll have $900.47 after 15 years. So my $500 became $900.47. For exponential decay, right, I have another problem. Coffee cools by 12% each hour. This is decay because it's cooling, meaning that the temperature is going to decrease as time passes, right? I have some information, right? It says that it's cooling by 12% each hour. And I also know that it's initially 98 degrees, right? So I'll start off with my initial temp, which is 98 degrees. And I want to know the temperature after an hour. So I'm going to need my rate of 12% divided by 100%. That gives me 0.12, okay, as my decimal. I'm going to take my starting amount, 98 degrees. I'm going to multiply it by 12%, and that's going to tell me how much the temperature is cooling from within the first hour. That's 11.76. This does not mean my temperature is 11.76. That would be way too little temperature, Remember, you're also going to need to, since it is cooling, subtract. So I'm going to take 98 and minus 11.76 degrees. And this is going to give me my temperature after 1 hour. That's 86.24 degrees after 1 hour. And again, I could keep doing this over and over. Going into hour 2, I'll use 86.24, multiply it by 0.12, get that amount, and minus it from 86.24. Then take that number, multiply it by 0.12, get that amount, minus that from that number that we had before, and keep going on this endless cycle. However, we know that we can tie it back into a times b to the x, right? If I'm going y equals a times b to the x, a is representing my initial amount, my 98 degrees, right? My base is how much it's cooling by, the thing that we're doing repeatedly, my 12%, but 12%, just like this, is not going to be my base. Just like last time, 0.04 is not going to be my base. Remember, we have this baseline of 1, okay? So what we're actually going to do is almost this. What we're actually going to do is, since we have that baseline of 1 and it is cooling, we're going to minus 0.12 and raise that to the x. Which what this really means is we have 98 degrees and I have this 1 minus 0.12, and I want to know what it will be after 6 hours. So we'll make our exponent 6. Using PEMDAS, right, we're going to need to simplify these parentheses first. 1 minus 0.12 just so happens to be 1 second. 1 minus 0.12 is 0.88. So using PEMDAS, I get 0.88. Do we agree that that is a decay base? Totally. We still have our exponent. We still have the 98 in front. So now we've done P out of the PEMDAS. Check. Now we have to do the exponent. That means we have to figure out what 0.88 to the 6th power is. Let's go into our calculator. 0.88, raise it to the 6th power, and I get this crazy decimal. Remember, don't write this all out. Just multiply it. That's the next part of PEMDAS, right? We've got the P, we've got the E. Now we're going to multiply or divide. We're multiplying 98 times it. So go in here and multiply by 98, and boom, I got 45.5116, all kinds of stuff. I've got 45.5116, ... continues on, right? And when it comes to money, actually, this is degrees. I could round, but I'm just going to say, let's pretend it's money right here. I look to this, I'm not going to round it up. So my temperature after 6 hours is 45.51 degrees after 6 hours. Okay, so I hope you're starting to see how things are coming together, how things are relating back to exponential growth and decay. Just a reminder that we know this to be true. We know the bases are either going to have to be bigger than 1 for growth or less than 1 that in decay, and that was happening, right, in our last exponential growth and decay problems. We also know that we're either repeatedly multiplying by a value or repeatedly dividing by a value when it comes to growth or decay, and that base helps us figure out what that is. And we have our initial value at the start, right? Which leads me into this. We know a times b to the x, and what we're leading into is something a little more realistic and a little more complicated, this. What do you notice? And what do you wonder about these two equations? How are they related to one another? What do you notice is the same? What do you notice is different? What do you think is happening? Hopefully you notice that there's a number in front of the parentheses in both equations. These are going to represent the same thing. We'll talk about that in just 1 second. I think another thing you'll probably notice is that both equations have parentheses. We know what b represent, that's our base, right? And in our more complicated equation, we have 1 plus r or 1 minus r. A question you might have had is like, what the heck does this mean? This means either you're adding or you're subtracting, plus or minus, okay? And those are kind of going to behave the same. And you might notice that there's an exponent. The letters changed, but they still have the same kind of skeleton. So let's put it all together here. We're going to use this equation based on what we know about growth and decay. So A is basically like our y, right? This is going to tell us the amount that we have. P is a really fancy word for principal, which typically we're talking about money and things like that. So principal is just a really fancy way to say our initial value or starting amount. Okay. R is going to be our rate, right? Specifically as a decimal, just like we've been doing, where it's going to be the part over the whole, or the percentage divided by 100. And T is going to represent time, okay? So typically we're going to talk about like bank accounts and things like that, or a certain number of months is going to pass by, or a certain number of years, or a certain number of decades, right? But it's just talking about time. So, and I guess another piece is if something is growth, we're just going to add 1 plus the rate, and that will give us a base bigger than 1. If we're talking about decay, we're not going to add, we're just going to do 1 minus our rate. That's going to give us a base less than 1, and that will match what we have. So we have like 2 little examples to go. An account at a bank has $1,250 in it. If the interest rate is 3%, how much will be in the account after 19 years? Okay, so first things first, I like to ask myself, is the situation growth or is the situation decay? We're talking about money in an account, so more often than not, this is growth, right? That's growth. So that means we're going to do 1 plus the rate, okay? I like to give myself that little note. If we're growing, that's 1 plus the rate. That's going to give me my base larger than 1. Then I just like to write out what we have from the word problem. So A, we don't know what that is right now, but I do know P, my starting amount, right? My account at the bank has $1,250 in it, so I like to just put $1,250 right here. I do know my interest rate is 3%, right? So I'm going to do 3% divided by 100%, and that's 0.03 as a decimal, okay? And I'm going to need my time, which says how much will be in the account after 19 years. So my goal is to figure out what exactly is A. If I start off with— I know that it's a growth situation because I have my bank account growing at 3%, and the goal is to figure out what's happening after 19 years. So let's set it up. I have A equals P times 1 plus R to the T since it's growth. I get to ignore the minus. And let's set up what we know. We know what P is. It's 1250. We know that we're going to have 1 plus because it's growth. And I do know my rate, 0.03. And the amount of time that we have is 19. So this is the setup. Cool. Now all we have to do is punch it into our calculator and use PEMDAS to simplify, which means we're going to have to start with our parentheses. 1 plus 0.03 is 1.03. That's nice and straightforward and easy. Then we're going to need to do the exponents, 1.03 to the 19th power. So we're going to go to our calculator, 1.03 raised to the 19th power, and I have this crazy thing. When I go back to PEMDAS, M multiply is next. So now I'm going to need to take this amount and multiply it times 1250 in my calculator. So multiply times 1250 in my calculator, and this is what I end up with. 2191.8825. I want to round this as money, so I'm going to put a box around this. Since it's 2 afterwards, my final answer is going to be 2191.88. That's how much money I'll have after 19 years. Okay. Then the last problem, a value of a car depreciates at a rate of 7% per year. The car initially had a value of $42,563. How much is it going to be worth after 11 years? This problem is going to be decay. Why? It's saying that the car depreciates in value, right? So this means I've got a 1 minus R situation, okay? What is the rate? It says it depreciates at a rate of 7%. 7% divided by 100%. That gives me my discounting rate of 0.07. How much is my initial value or starting amount of the car? The car initially had a value of $42,563, so 42,563. And the amount of time that's passing, I want to know after 11 years. So again, I want to find out what the amount is. Set it up in our situation. Our amount is our initial value of the car, 42,563, times my base, which is, since it's decay, I'm going to do 1 minus my rate, 0.07. And the amount of time that I'm interested in is 11 years. Again, we're going to run it through PEMDAS. Starting with the parentheses. Parentheses, we need to simplify 1 minus 0.07. All right? 1 minus 0.07 gives me 0.93. That's my parentheses. Then we're going to need to do our exponents and then multiply. So parentheses, we simplified. Now we need to do the base to the exponent. That's E in PEMDAS. So I'm going to do 0.93 raised to the 11th power. And that's this crazy decimal. Don't write it down. Just know that our next step is we're going to need to multiply this number times it. So times 42563. 42563. We get 19,157. 19,157 point, where's my decimals? 7572. 7572. Since this is money, we're also just going to round to 2 decimal places. Since the third number is 7, if it's 5 or higher, you round 75, the number in the box, up to 76 cents. So it's going to be 19,157.76 cents is our final answer, is our amount of the value of the card. 19,157.76 is the value of the car after 11 years.